Okay, so before we start delving into the analysis of sequences, the series, we need to uh, define rigorously the intuitive notion of a sequence. This is section 2.2. In the book. So what is a sequence? A sequence is just a function from n to something. It could be real numbers, could be C, it could be complex numbers, or any other field. So a sequence is a function whose domain is n. For example, you can consider the sequence one, 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 etc. The function need not be injective, so this is the constant sequence. Just like you have constant functions in R, you have a constant sequence. Remember that sequences are functions. The only thing special about a sequence is they are functions from n to some other some other set. So it's a constant sequence. Then you can also have, so this is example A, or 1 if you want, number 2, say the sequence 1, 1, 1 over 2, 1 over 3, 1 over n. So this is the nth term, etc. Another example, so we usually write sequences like this. This is an example given in the book. 1 is equal to 2, and x2, no, xn plus 1 is xn plus 1 divided by 2. So you can also define, there are many ways in which you can define a function. And you can define them explicitly, just give me all the terms. There could be no relation between the terms, something completely random, or there can be a formula, like in this case. Like in this case, for instance, the first one, or it could be a recursive formula, like in this last example 3. I mean, I also pointed to this as being an explicit thing because from this relation you can actually retrieve a very explicit expression for xn plus 1, for xn in general. But sometimes, yeah, I mean, you will be given sequences which are presented to you in defined in a recursive way. So you define the first, say, 2 terms, and then you define the next, all the other terms by means of a function that depends on the 2 previous ones, just like in the case of the Fibonacci sequence. And now, the important thing here about sequences is actually what happens when n goes to infinity. The first terms in a sequence actually are not really relevant. Most of the statements that we're gonna be discussing now have nothing to do with the first term, so we don't actually care. So all the properties that we really care about about sequences have to do with what happens beyond a certain point. So is this function, is this sequence really small beyond a certain point? Just need to find a very large number n, after which all the elements in the sequence are smaller than, say, some epsilon, and or if the in that issue the sequence is non-negative. If it's allowed to take on negative values, you want to say that it converges to zero, then we want to say that beyond a certain n, for larger values of n, the sequence is trapped between minus epsilon and epsilon. Okay, so those are things that have to do with what happens, let's say, when n goes to infinity. And the most important thing, I mean, for mathematical for mathematicians, I mean, the most important concept related to these sequences, at least for analysts, is the convergence or not of a sequence. And so given a sequence a sub n, we say that it converges to a real number a if well, I'm gonna write it using notation we've gotten used to. For every epsilon greater than 0, there exists an n in n such that, and this is what you need to show whenever you want to show that something converges to a given number, such that for all n greater than or equal to this n here, we have that the distance between all the terms a sub n and a is less than epsilon. So if that's what I was referring to. So this whole thing just tells you that no matter how small a number is, a number epsilon, if the sequence converges to a, I mean, it can oscillate. It can take on greater values in a. It can take on smaller values of a. It can, maybe it's oscillating, so it's not always getting closer and closer necessarily. But beyond a certain point, so beyond this n, the values of an are trapped in an epsilon's neighborhood of this small number a, which is the limit. Okay, so the idea of getting closer and closer that you learned in calculus is not quite right. The right way to think about it is that the sequence is going to be trapped between arbitrarily small neighborhoods of the limit, provided you pick an n that is large enough, and so you consider only the terms that are the terms in the series in the sequence for n greater than this specified value, beyond which this property holds. And to indicate, now the important thing is to indicate an converges to a, we write either lim of an as n goes to infinity is equal to a, an goes to a as n goes to infinity. These two things encode the same information, so there's nothing different about these two things. I mean, they say the same thing. And the important thing here, I mean, at least as far as the course is concerned, it's not whether you know remember this definition by heart or not, but whether you know how to apply it. So that's the important thing about it. Here there's a discussion about the neighborhoods of a point, which we'll not get into. I mean, this doesn't actually. I mean, this is an insight that is not really useful when you're doing just real analysis. For general topology, perhaps, but everything we're going to be doing here has to do with metric spaces, so we just don't need to be concerned by these things. You should probably read it and be aware of these things, but none of the problems that I'm going to ask you to solve, I mean, require you to know, I mean, this language or be familiar with it. The important thing now is how to show that something converges to something else. So this is the idea how you proceed. So this is a model problem. So you're going to be asked to show stuff, I mean, to prove statement like this, prove that or you know what, I mean, I'm just going to give this to you as an exercise, a small exercise first. So the mission is going to try to do it on your own. So consider the sequence AN, where for all n in N, and in N a sub n is equal to 1 over the square root of n, like they have in the book. Now show or prove that, we have to prove rigorously, not only show me that that's the case. So prove that the limit of an, as you probably suspect, so it goes to infinity, is equal to 0. So prove this fact. As n approaches 0, the limit of an is actually equal to 0. So what is the task? So what is the solution here? So this is how we always begin. We let epsilon be greater than 0, be an arbitrary number. It's fixed from now on. This is fixed from now on. So now that you started with this, I mean, epsilon is going to be fixed for the rest of the argument. Okay, so epsilon is going to be fixed. But you have to pick an arbitrary epsilon. You don't have a choice for epsilon at the beginning, but once you said, I'm going to take this epsilon, I'm going to consider any epsilon. Just give me any epsilon. This epsilon is going to stay like that for the rest of the argument. Now you can go back and you can say, of course, since epsilon is arbitrary, I've shown the proposition. You need to show this thing, that for every epsilon. So you just pick one epsilon, an arbitrary epsilon, and now you need to find an n in n such that the rest holds. Okay, so start by picking an epsilon. Now the task is to find an n. No. Task is to find this big capital N. Remember, you have an epsilon, and then you need to find an n. Given that epsilon, that epsilon is just a placeholder for any value of epsilon. So epsilon is fixed now. You need to find an n that will depend on epsilon, in which you're going to have an inequality. So find n. So how do we find that? Well, we first notice that this function here that 1 over square root n is decreasing. This is very important for what comes. So why is this important? Because then this is going to allow us to find one n beyond which all the other terms are smaller. Because I mean, if one term is smaller than epsilon, something smaller than epsilon, and all the other things are smaller than that term, then you're done. Why is this decreasing? So let's look at what happens with the n plus 1 term. So this is what we want. So indeed, 1 over the square root of n plus 1 is less than the square root of n. Because the square root of n plus 1 is greater than the square root of n. If you divide both sides by the product of these two things, then you get this thing, which is a positive number. The quotient of these, the product of these two things is a positive number. Then you obtain this inequality here. And this follows from the fact that the square root of x is increasing. So let me see. So f of x, I'm going to write it more formally. Is, this function is not defined for negative values, is increasing for x greater than 0. You can include 0 if you want. Now, why is this true? Okay, so maybe I should stop here a little bit to make sure we are on the same page. So a proof along the lines of, well, if I ask you to show that this is actually increasing, you cannot just tell me, okay, f prime of x is equal to 1 over 2 times the square root of x, which is positive. This proof will be incorrect. I mean, we're just doing we're redoing everything we did for calculus. We're starting from actually constructing the real numbers, so we are not allowed to talk about derivatives yet. Okay, so this is not an acceptable proof. However, what we can do is say, and we actually only need this for, okay, so the square root of x plus 1 minus the square root of x is greater than 0 if and only if the square root of x plus 1 minus the square root of x times something positive is greater than or equal to 0. In fact, this is going to be greater, strictly greater. Remember, if we multiply, this is one of the actions we had before our operations in this field. If we multiply by multiply two positive numbers, we get a positive number, and we multiply one negative number by a positive number, we get a negative number. And so this is true here if and only if this is true. This number here is positive. So if we obtain this statement here on the left by multiplying by this factor on both sides. And since that was so we obtain this statement from the right, assuming the statement on the left by multiplying by this factor on both sides. And conversely, we can divide by that. This is of course non-zero because this is at least 1. Remember, the x is greater than or equal to 0. So those two statements are equivalent, but then this statement here becomes x plus 1 minus x is greater than 0, which is of course true. So we know now that the square root is increasing. I mean, at least on n. But you can adapt this proof. I mean, there's no reason to include 1 here. I mean, to put right 1 here. Anything positive here, you will arrive at the same conclusion down here. So you can show that then the square root is an increasing function for x greater than or equal to 0. And one thing that we did here is that the square root of x plus 1 squared was equal to x plus 1. That's because we're on the positive side of things. I mean, if you take the square root and raise it to the square, the square root is always a positive number by definition, but in fact, it has nothing to do with that. I mean, the square root is a positive number, but when you square any number, you get a positive number. But what is this equal to x plus 1? Why not say minus x plus 1? Well, x plus 1 or the square root of a number makes sense if the what's inside it was a positive number. So if you raise it to the square, and of course you're going to get what's inside since it's a positive number. And so now we know then that this function is decreasing 1 over the square root of n. And okay, so this is what I wanted to make sure you understand. You would understand. So if we have something like the square root of x plus 1 squared, you cannot just cancel out the squares here, or the square and the square root. Okay? If x plus 1 were a negative number, say, then x plus 1 squared would be a positive number, and then you would get here the absolute value of x plus 1. Here you're multiplying the square root of x plus 1 times the square root of x plus 1, which are both positive numbers, and then what's inside is also a positive number. So you don't actually need to write this down, but instead just know the fact that you take the square root of something squared is always equal to what's inside. Because what's inside has to be positive. So no need to bring the 2 inside. Okay, but that was the point. So the whole point right here was just to show that this function here was decreasing. 1 over square root is decreasing. And why do we want that? Because that will make it easier for us to find n. Remember, we picked an arbitrary value of epsilon positive number epsilon. And now, so what do we want? One is to find a number in n such that the absolute value of a sub n minus 0, here a is equal to 0. This is what we're trying to show, that the limit here is 0. So that means that a sub n is less than epsilon. But all the a sub n's are positive, so this is equal to a sub n. This is just in this case. So we want to show that there is for all n greater than or equal to n. So we want to find a value of n such that a n is less than epsilon for all n's greater than this capital N that we're supposed to find. Now, if we find just one n, find say an n0 such that n0 is less than epsilon, a sub n0 is less than epsilon, we are done. Why? Because if n is greater than n0, since we know that the 1 over the square root of n is decreasing, we have that a, so n0 is less than epsilon, which in turn is going to be, remember this is just equal to, sorry about that, so this is exactly equal to 1 over the square root of n0. But since the function is decreasing, this is going to be greater than 1 over square root n, which happens to be a sub n. Just by finding one n0 such that a sub n0 is less than epsilon, we'll get for free that all the other subsequent a sub n's are going to be less than epsilon. But being less than epsilon is equivalent to this statement right here, which is the statement about convergence. So this is the whole point. We just need to find one value, n0. And that n0 is going to be Rn. The n we're looking for. Perfect. So how do we find that n? Now that a n0. So we want 1 over this. So what we want is to find an n0 such that a sub n0 is less than epsilon. But this is equal to, as we wrote up there, 1 over the square root of n0. And this is so this will be True if and only if. So you can divide by epsilon. Remember, epsilon is not equal to 0, and it's positive, so we'll not change um, the the order of symbol that tells us whether something is bigger or not than some other quantity. The greater sign is going to be pointing the same direction. So the square root of n0 is greater than 1 over epsilon. So we can divide by epsilon and multiply by the square root of n0. And this again is equivalent to the statement that 1 over epsilon squared is less than n0. Why is this? Because the function x squared is increasing. It's increasing for x greater than or equal to 0. Again, I mean, the proof here is much simpler, actually, than for the square root, because, I mean, you simply expand and you'll see that, I'm going to do it in the natural numbers. You can replace this 1 by delta, and well, in fact, let's do it with delta. So if you have a number that is bigger than x, so x plus some delta squared minus x squared, this is equal to, remember the binomial, x squared plus 2 delta x plus delta squared minus x squared. Two terms cancel out, but delta is positive, remember, because you're adding something to x, you're making it bigger than x, and x was already positive because we're only considering f of x where x squared where x is greater than or equal to 0. And this is x could be 0, but then still, I mean, you still have this term delta squared, so that is greater than 0. So that means that the difference between x plus delta squared and x squared is positive. So I mean the function is increasing, so it's always going up. Again, don't use derivatives yet. I mean, this is not this is not allowed at this point because we're reconstructing everything. What we can do here is say, okay, now that we know that the function is increasing, and we've already shown that the square root is increasing, if we start from this side, we just apply x squared on both sides, and we know that this is gonna preserve the way the greater than sign is pointing, and vice versa. As well, if you start from here, just use the property that the square root is increasing. Okay, so so now we reduce everything to finding an n0 such that this thing holds. Remember, epsilon can be arbitrarily small, right? So how do we know that there? I mean, we're not going to find exclusively an not, but we can know for sure that there's one n not. Why? Do you remember? Yeah, it is the Archimedean property. So we know this is the Archimedean property. And if we go back, so we found such an n0, and that n0 is going to be our n, Why? Because if this is true for some, this is true here for some n0, then all the other n's, the n's that are greater than n0 are going to satisfy that a sub n, see here, that a sub n is going to be smaller than epsilon. But going back, a sub n being less than epsilon is exactly the same thing as saying in this particular case that the absolute value of the difference between an and the limit that we're trying to show is the limit for an is less than epsilon. So we have actually shown the property. And so this is what we're going to show, and so this is the end of this illusion. I will give you some other things some other problems to work on. There are some applications where you don't necessarily have this property that the sequence is going to be increasing or decreasing. However, or where things are not necessarily so simple to invert, like in here, we just take the square root. I mean, you have the square root, so you take the square and you find an n. Maybe it's not going to be so easy to solve, say, for n0, or to put it in a way that it just depends on is it just a consequence of the Archimedean property? So we need to bound things, find bounds for the expressions we have from above or from below. But once you learn that, you'll be able to do all the problems of this type with this is not going to be inconvenient for you at all. Okay, so that's what we're going to do the next